And as it absorbed the heat energy, my paper did not get hot enough to set on fire. That means that this one has to be my alcohol. Let's see how well alcohol burns. There we go. Wow! So this alcohol for ethanol burns about 2,000. If my paper did not burn in water, but it did burn in alcohol, if I were to mix these two liquids together, does anyone have a prediction? What do you think? Sorry? It might burn as well. It won't burn, okay. So opposite predictions, let's see what happens. Well, it's definitely a fire, but my paper is still there. So you're both right. So what happened there is that my alcohol burnt away at a really high temperature, but my water absorbed all that heat energy, therefore protecting my paper from setting on fire. It's a bit like a Christmas pudding. You kind of burned away the alcohol, but the rest of the pudding is still there. The other one is water. Now this thing is kind of joined together with other elements to make some chemical reactions. It's a bit like Lego blocks, kind of joined together in different ways to make different materials. And speaking about carbon dioxide, we normally experience, and it's really cold, it's minus 78 degrees Celsius. It looks a bit like snow. There we go. And the thing about carbon dioxide gas is that it is colourless. You can't see it. But you might notice there's a white misty effect in here. That's because the dry ice, due to it being soaked around it from a gas into a liquid, and then eventually that cloudiness goes away because those water droplets, they evaporate and become. See what happens. You should notice that the bubbles are floating. You see that inside my box? It's floating on that layer of heavier carbon dioxide gas. And if my bubbles survive long enough, they do get bigger and they do sink down. That's because the carbon dioxide gas inside the box, that when you put your paper in water, it doesn't set on fire. That's because the water is very good at removing that heat element away from our fire triangle. So you can use water in fire extinguishers, but is it always a good idea to spray water over every single type of fire? Because water is a very good conductor of heat and electricity, which means it's very good at carrying that heat electricity. You might get an electric shock, you might get electrocuted. So in terms of electrical fires, I'm going to scoop some of this invisible carbon dioxide gas, which is inside my box, and as it's heavier than air, it should still be in the beaker. And if I pour this over my fire, it goes out. You see that? It goes out because the carbon dioxide is pushing the oxygen out of the way, therefore putting it out, as it removes one of those things in our fire triangle. And I mentioned the word conductor. What it is, it heats up a lot faster. Now, most things go solid, liquid, gas. Carbon dioxide solid goes from solid straight to gas, and we call this sublimation. This white cloudy stuff is liquid water droplets, okay, due to it being so cold. And for a bit of fun, I'm just going to make some bubbles. So here are some standard bubbles to begin with. This is just a metal coat hanger that I've bent in this shape. I tie some string around it, and then we have ourselves a bubble wand. And with this, I can make some bubbles. And as you can see, my bubbles, they are very, very floating. And earlier, we saw that carbon dioxide gas is heavier than air. So if I trap some carbon dioxide inside a bubble, do you think my bubbles will be more floating, or do you think they'll be heavier and sink down faster? What do you think? Heavy.
Ready.
You can see they're definitely sinking down faster than before. Yay! Awesome. Guys, and hopefully I can make a little volcano. And it reseals itself if I remove that side. Sorry guys, can you go back to your seat for me please? With gases, we call these the states of matter. So my dry ice here, my solid carbon dioxide, solids don't take up much space, they have a nice regular arrangement. Liquids like my bubble mix, they fill up the container that it's in, how much it fills up anyway, and gases take up a lot more space. Just to show you guys how much more space gases take up, I'm going to add this in here, and my bubble mix will trap the carbon dioxide produced. So from a single spoonful of solid carbon dioxide, how much gas do we get? Awesome.
Is that good?
And as you can see there, gases take up a lot more space compared to both liquids and solids. Excellent. It's cool, right? Now as that is dry ice, minus 78 degrees Celsius, I'm going to show you something even colder. I'm going to show you something called liquid nitrogen, 196 degrees Celsius. I'm going to pour some out into a beaker and show it around. But this is liquid nitrogen here, and it's boiling away at room temperature. Celsius, it begins to turn into a gas. Different materials inside my liquid nitrogen to see how it affects the properties of a material. By properties of a material, I mean how something, and it has a yellowy, I just put this inside for now. That's my egg. The next thing I'm going to put that inside. The next thing I'm going to put inside is, now as we said earlier, gases take up a lot more space compared to both liquids and solids. So if I put my balloon inside my liquid nitrogen over here, and my gas begins to condense from a gas into a liquid, and some of it might even freeze into a solid. And the balloon deflates, it gets smaller. Make sure it goes all the way. And in a moment, when I take this out, all that frozen air and liquid air, just shake it around, the heat around us is going back inside our balloon and turning all that gas that was a liquid and a solid back into a gas. Shake it and inflates our balloon once more.
Wow.
There we are. Once again showing that gases take up a lot more space. A jelly sweet, a jelly worm. Now the main properties of a jelly worm is that it's sweet, but these ones are also very flexible. There's my little jelly worm there. They're nice and stretchy, they're floppy, nice and flexible, right? Let's put this in my liquid nitrogen and let's see what happens. It doesn't take a long time. Let's have a little countdown from 10. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Very good. Now here's my jelly one. Now I'm just going to drop this and let's see what happens. Oh! In case you missed that, you can see that my jelly worm has shattered.
What happened?
It broke apart into lots and lots of tiny pieces. So what happened there is that, sorry guys, can you not touch the table for me please? Thank you. Well, let's see you're right. Oh, you're right. It's now, it's now as hard as a marble. So normally we took so much energy away from it. The things that make on my basketball can no longer move about, and it's super hard. But we regain its bouncing, so it's a good conductor, so it heats up faster than if I just leave it up in the air. And hopefully when I go back to that, it will regain its bounciness. Let's bring out our final thing. Does anyone, you guys are right. And you might have also noticed that when I put my object inside my liquid nitrogen, there was always a lot more initial mist, yeah? That's because the heat from our objects go into my, always moves from hotter to colder, never ever colder to hotter. So in winter time, sometimes you might hear the phrase, close the door, you're letting the cold in. That's incorrect, you're actually letting the heat out. Okay, let's bring out our egg. This is my egg over here. It looks very similar to before, apart from a bit smoky. Let's give it a little tap with my hammer and let's see what happens to it. So normally your eggs are very break up very easily. But you can definitely hear that's a lot harder.
idea. It's hard.
Please don't touch it. But you should notice that my raw egg, it melted. Can you see that? But my raw egg, it now looks cooked, but it is in fact still raw. So what happened?